Hmm. Incorrect. Oops. You always check if you've made it. Once you've made a mistake, always check if there's a way to treat it as if it was a success. If there's a way to change the rules so that it was in fact a successful idea. You never know. I'm going to shift my quantification up a little bit so that this is going to include for all D. So we get alignment between the quantifications. Okay. Yeah, we didn't simplify this all the way. Which now maybe in retrospect we shouldn't have simplified either, but now that I've simplified one, I need to simplify the other. Okay, let's... I'll do a simplification step in the transfer. That's going to be a little bit confusing. extra bracket. Actually, turns out we did need that extra bracket. I think. Okay, now the question is, how do we write this so that we can pattern match it most readily? Well, these are associative or wise. These three terms. Are they, though? No, maybe not. No, they're not. No, I might need to distribute both of them, actually. Let's do a... might need to do a lemma here. If we're not going to use that there. Alright. Lemma here. If I have P if I have P, then Q if and only if R. This is interderivable with the expression, not P or no, I don't think that's the way to take this limit. Let me see. Take this first step, because we don't really need to reduce this part. So we'll say P, then Q if and only if R and P. Okay, which is interderivable with the expression P, then Q, then R, and R, then Q, and P. Okay. Which I can get P, then Q, then R, and P, and R, then Q, and P. No problem. Why do I care about that? Because I can also have an R is an element of A in the first expression up here. Do I need R as an element A in the first expression? I'm not sure yet. How many pages are left in these? I'm about to have to break out another notebook. So what this actually is a source is associative and-wise. It'd be P and so this should be bracketed here. close, so we need another open over here, actually. And then this would be a second close up to here, and then a third close up to here. Okay, and then we dissolved brackets here, but actually, no, yeah, that's fine, but we still need another bracket. So close two brackets, and R is an element of A. And then we close this bracket, and that closes up to the beginning. So we have open, close. Then wait, why did we need two brackets? Yeah, yeah, we actually did need three brackets at the beginning. The point is, how did I? Open, close, and then open, close, and then we need a third bracket at the beginning because we need to close the entire thing for this OR. Okay, so now open, close, open, close, open, close, and then this closes the entire thing. That's kind of horrible, but whatever. And now, yeah, the contents of here to here are associative and-wise. P and Q and R and S or T. So I could distribute the OR. Whether that is a good idea or not is unclear. Is there a better way of writing this out? If we're going to get so we can distribute this R as an element of A and thereby get, and then distribute this R as an element of A through, and then step down this and we thereby obtain these two terms. Okay. And then we would also step down this and, I suppose. We might actually need that. No. Because this term, the corresponding term, not E is an element of J or not J is an element of A, we're actually going to get from distributing this or, not R is an element of A. Okay. So I'm going to take that step. Alright, and we're going to use, I guess this will be our new color rule. Do I need to do anything with this R as an element of a term? And why did I introduce it if not? It looks like we do need to distribute that. Okay, and the reason is that we need it distributed specifically to this. D is an element of R. Okay, and that will give us the term E is an element of H and H is an element of A. Alright, so we'll do this will be okay, and okay, so yeah, we specifically need that on this term, so everything else gets handed down in the path. Okay. Alright, so leave some room for brackets. Well, we almost certainly need that bracket, so we'll just do another one over here. Sure, and then we have room for 2 or 3 more over there. Alright, so not D is equal to the ordered pair ST. Okay. Or is an element of R. Or D is an element of R, and R is an element of A. We're writing it out like this because it gets us closer to this. Makes pattern matching easier later. Yeah, I have to get more willing to introduce negative space if it makes things more legible. We're learning a valuable lesson here. Okay, so now open, close, and we'll certainly need one more at least. Alright, and now we're going to have where's the statement about? Okay, so D is equal to the ordered pair PQ. That should be Spanish orange, which makes pattern matching easier. Alright, let's see. D is equal to the ordered pair PQ. Okay. And the ordered pair PR is an element of R, and R is an element of A. And the ordered pair RP is an element of R. Nope. QR. And R is an element of A. Get my scratch. If I have P, then Q, then R, and S. Okay. Interderivable with not P or is that associative or wise? If that is associative or wise, then let's see. Well, I guess we have to appeal to the truth tables because it's rare that we bother appealing to a truth table, or it's rare that we find it useful, but that's the only way to resolve a question like this, so I guess we'll make a truth table. I feel like the truth table is going to say, yes, these are the same. Okay, but the point I'm making with this expression is that if these are associative or wise, then these two expressions are the same. And that doesn't seem unreasonable. It's like currying, except that we don't care about the order where we receive arguments. Okay, but a truth table for this is absolutely horrible. I guess I can find out if there's an internet truth table generator. Or I could just ask, is okay, though. This is saying no, but this is also not representing the statement in the way. How do I do? Yeah, I feel like it's not going to be able to parse this. Yeah, so this is, yeah, makes good sense. This is already what we were expecting. It's just it's or-wise associative at this point. And the R, it doesn't make any difference that this is R and S instead of just R. Okay. Well, and that's convenient. That's what we needed to be true here. Okay. What do we do with this being true, though? Let's see here. Yeah, why did I care about that? That's less clear, I forget. Okay, let me think. Dun, dun. Okay, let me think through these brackets again. So we have open, close, open, close. Okay, we have open, close, and now this will need to be open, close, then we need another for or not D is an element of R. Alright, so now open, close, open, close. This is open for the entire thing. We close that, and now we have or not R is an element of A outside of all of the brackets. Okay. And what do I want out of that? So we have these two expressions are now equivalent. The orange quantified expressions are equivalent. Not E equals the order pair PQ, not D equals the order pair ST. No, not yet equivalent. We would need to distribute this through, but that's the problem. Because when we distribute this through, these are two terms ANDed together. So this is P and Q or R. P and Q or R. And then when we distribute the or R, it will be R or P and R or Q. There might be a horrible hack to get around this. thinking here? Well, so if I distribute this OR expression, it's not a problem. Well, no, it is actually a problem. No, it's not a problem up here because then it would just be associative OR-wise with each of these terms. So I don't have to distribute this not R as an element of A through orange. I can distribute it to orange, duplicate it, and give a copy to each of these two terms. Okay, and then I just don't give a copy to these two terms, and then we complete the creation of the orange expression up here. Okay, the problem is that I can't do the same thing for this. No. However, there's a copy of. I can get a copy of R as an element of A back here. Or so to say, when I distributed this, I didn't get rid of it. We can pretend. Okay, so what's the idea there? The idea there is that let me think here. So we have not R as an element of A. We OR distribute it through this expression. I'm losing it. I'm thinking what we might be able to do is take advantage if I claw back this and R as an element of A, then we would have not R is an element of A OR'd onto this expression. I can turn that into the conditional and then have R as an element of A. I'm not sure that's real. Yeah, well, we're not going to be able to confirm. We're not going to be able to confirm any of this anyway. So, okay. So, let's do the first stage of that plan. Okay, so P or Q and R. Okay, so that'll be interderivable with the expression. We're using the wrong letters. This should be S and T. I got confused at some stuff. Well, it doesn't matter actually. I mean, it really just doesn't matter. Because we're doing pattern matching anyway. It's a little bit rough, but whatever. Not the ordered pair PR is an element of R, or not is an element of A. Okay, or yeah, this should be okay. I don't know. This is getting the complexity of this proof is higher than actually the last 2 or 3 proofs we've had to do are much higher than anything we have to do throughout the rest of the book up to this point. So it's a little bit harder to track. Or not the ordered pair TU is an element of R, or not R is an element of A. And I'll give myself okay, and then or D is an element of R, and R is an element of A. Alright, and I think I will do pattern matching on that entire term in this step. What do I mean? Just so we can close out this and. Okay, so right, and then I will say and we're going to store this in blue, true blue. Okay. And now the question is, what horrible thing do I have to do here? If I give this diagram blue, then I will have not light cerulean blue or diagram blue. Okay. Oh no, that was the point of, no, hold on. Because this gets distributed. Yeah, this is. Yeah. This doesn't need to be done. And the reason this doesn't need to be done, this is associative OR-wise. We distributed through, and now we have not R as an element of A or this entire expression, but then that's associative OR-wise. Ah, we did it. Then we ended up getting, yeah, we might want to redo this. We also might not want to redo this. Alright, so we're going to have interderivability, blue, and getting a little bit messy at the end. Oh well. So D is equal to the ordered pair PQ, and the ordered pair PR is an element of R, and R is an element of A, and the ordered pair QR is an element of R, and R is an element of A. Okay. Or I guess for pattern matching we do want that there. And not D is an element of R, or not R is an element of A. Alright, so the remainder of the pattern matching here. Where did I put? Oh, there it is. Okay, so so this gets notebook management errored out. Okay. I'll just keep going in the standard ordering here. Okay, there's your proof. Proof by pattern matching. technical bit. This would step down. I needed to. Oh well. There exists an H. Such that D is an element of H is an element of A, and then similarly this would step down. Yeah, that wouldn't step down because this is already for all J. Okay, and there's your proof. Do we want to redo that one? I will see if I have the energy for it. And we complete the last of this sequence of exercises. I'll leave that on screen. I am going to step away for a moment. Be right back. Okay. Let's start the last one. Our last chance to do one of these without the whole thing disintegrating into noise. Alright. Alrighty, so what is exercise 20E? For all R, if we begin with the expression for all R, if R is an element of A, then R slash R converse is equal to R. Then we may derive the expression the big intersection of A slash the big intersection of A converse is equal to the big intersection of A. Can we derive it? Well, we can always throw some sleight of hand in there, if we need to. Okay, so naturally enough, we will start from the left-hand side. Okay. And I'll just give myself the conditional equivalence immediately. Okay, so and I'm combining for all D into this. Prenixing for all D into that. Okay. D is an element of R slash R converse, then D is an element of R, and if D is an element of R, D is an element of R/R converse. And R is an element of A. Or not R is an element of A. Okay. So I will say not these brackets. I'll just do one bracket at a time, and then I don't have to care as much. Not. There exists an S and there exists a T such that D is equal to the ordered pair ST, and there exists a U such that the ordered pair SU is an element of R, and the ordered pair UT is an element of R converse. Or D is an element of R. Okay. And now the trick we're going to do here is this is going to line up immediately by doing there exists a P and there exists we could do no, never mind. Okay, there exists a P and there exists a Q such that D is equal to the ordered pair PQ. Exists an R such that the ordered pair PR is an element of R, and the ordered pair RP is an element of R converse. Or not D is an element of R. Okay. Open, close. Open, close, open, close. I think here. What did we prove earlier? So we can give a copy of and R is an element of A to each of these, but we have to. I think like scratch. No, not scratch. Rather, let me get out this lemma. Yep, that is indeed the conclusion we reached. Hopefully we applied that consistently. No knowing whether we did. We could store it, especially since we're running out of left-right room. Okay, do I have a color that I want to use? Do I want to commit to using this? I guess so. Alright, so, and... yeah, we could do this. Okay, and then it would be here, and... I put it inside the brackets, I'm not sure that makes sense, but whatever. Or not R is an element of A. Alright, so now, what are we doing? Let's get rid of these quantifiers, and then maybe we can get these expressions back in. So orange, Spanish orange. Alright, and then I guess we'll just have to know that this negation gives us for all terms. Okay, so we're gonna have not, let's get, it might be enough bracketing room, or it might not, but okay, D is equal to the ordered, not D is equal to the ordered pair ST, or not the ordered pair SU is an element of R. Yeah, well, we don't have a reason to structure this any different. We obtained the reason to structure differently back here from the right-hand side, where when we had this OR expression that we don't have, we needed that. We needed the line break. I think I screwed this up, actually. How, if so? Let me see here. I think we did a proof for big intersection and not big union, which is proving strangely difficult to confirm. No, we did big union. It would be, if F is an element of A, then The ordered pair is an element of F for intersection. Okay. I believe it. Alright, so we'll just keep going here. Or not the ordered pair UT is an element. No, we can go ahead and fix that. TU is an element of R. Okay. Or D is an element of R. Alright, so bracket 1, bracket 2, and R is an element of A. Yeah, it looks like we might not need to use that coloring. R is an element of A, close second bracket. Okay, and now we have and. Okay, and now we will have D is equal to the ordered pair PQ and the ordered pair PR is an element of R and the ordered pair RP is an, nope, PR is an element of R. Okay. And now close bracket here, or not D is an element of R. Okay, close bracket here, open corresponding bracket here, and here we will use blue. Okay, and now open, close, open, close, open, close, open, close, open, close. Or not R is an element of A. Okay. And that is the end of our left-hand side excursion. Now we begin our right-hand side excursion. For all E, which I will commit simply to red here, for all E, E is an element of the big intersection of A slash the big intersection of A converse. Then E is an element of the big intersection of A. the big intersection of A, then E is an element of the big intersection of A slash the big intersection of A converse. Okay. Interderivable with the expression there exists an LMNPQR. Right, there exists an L. There exists an M such that E is equal to the ordered pair LM, and there exists an N such that the ordered pair MN is an element of the big intersection of A. And the ordered pair in, not in, yes, in L. Okay, and L is an element of the big intersection of A converse. Okay. That needs a negation in front. Okay, and then I will open that bracket, close that bracket, or E is an element of the big intersection of A. Close that bracket, and there exists a P and there exists a Q such that E is equal to the ordered pair PQ, and there exists an R such that the ordered pair PR is an element of the big intersection of A, and the ordered pair RQ is an element of the big intersection of A converse, or not E is an element of the big intersection of A. Okay. Which is interderivable with the expression not E is equal to the ordered pair LM, or not the ordered pair MN is an element of the big intersection of A. Yeah, taking an extra step to do that is maybe a little bit excessive, but whatever. Or the ordered pair LN is an element of the big intersection of A, or E is an element of the big intersection of A. Open, close, and because there's no corresponding alteration here except for reordering that, but whatever. E is equal to the ordered pair PQ and the ordered pair PR is an element of the big intersection of A, and the ordered pair QR is an element of the big intersection of A or not. E is an element of the big intersection of A. Alright. So open and close, and then close here. So the same structuring is probably fine here. Sort of spatial page-wise structuring. All right, so not E is equal to the ordered pair LM or not. There exists an F such that no, this is for all F. This is where we were about to do the union again. For all F, if F is an element of A, then what's the definition of the big union? Or big intersection? F is an element of A, then the ordered pair is an element of F, I think, but let's check. For all B, if B is an element of A, then X is an element of B. All right. For all F, if F is an element of A, then the ordered pair Mn is an element of F. Right, this is showing, okay. The ordered pair Mn is an element of F. Or not for all G if G is an element of A, then the ordered pair Ln is an element of G. Okay. Or okay, so this is Open, close, open, close, open, close, open, close, open, close, open, close. So we need close here. No, not yet. After this term, right? Or for all h, if h is an element of A, then E is an element of H. Okay. And let's see. E is equal to the ordered pair PQ. Let's get E is equal to the ordered pair PQ, and for all J, if yeah, we probably excessively bracketed that, but that's just not excessively bracketed now. Okay, J is an element of A, then the ordered pair PR is an element of J. Okay, and for all K, if K is an element of A, then the ordered pair QR is an element of A. Alright, so even that might be a little bit excessive for bracketing. Less excessive than this, though. Roughly the same amount of excess, actually. Yeah. No. Okay, and then well, okay, so open, close, open, close, open, close, open, close, open, close, open, or not for all L keep getting lost here. We got not for all L if L is an element of A, then E is an element of L. Okay. And is that bracket erroneous? How did an erroneous bracket slip in? Let's find out. Let's see. Open, close. No, I guess not, though. This is excessive bracketing then, I think. No, because we have the and. This is horrible. Hold on. Open, close, open, close. Open, close. open, close, open, close, open, close. Okay, I don't think we need... Yeah, we do, because, yeah, this is an AND expression, so we do need the full open and close, so this will be the final close. All right. Okay, then what? Which is interderivable with the expression. Let's try to reduce the excessive bracketing here a little bit. That should be orange, but fortuitously that color's in the right direction. Alright, so not E is equal to the ordered pair LM. There's not really a good reason to misalign this, so let's cram that in. So this would be there exists an F. Let me get a little template here. Alright, so if we have not P then Q, this is interderivable with the expression not P or Q, which is interderivable with the expression P and not Q. Alright, so this will be there exists an F such that F is an element of A and not the ordered pair Mn is an element of F, or there exists a G such that G is an element of A and not the ordered pair Ln is an element of G. Okay. Now we would close bracket here. No, because this is all or wise associative, so or for all H, not H is an element of A or E is an element of H. Now we close this bracket. Okay. And Spanish orange. We don't need that anymore. E is equal to the ordered pair PQ. And for all J, not J is an element of A or the ordered pair PR is an element of J. And for all K, not K is an element of A or the ordered pair PR QR. Is an element of K. Okay, and now what do we do? All right, so open, close, open, close, open, close, and now open, and we have or. There exists an L such that not L is an element of A. No, such that L is an element of A and not. The ordered, and not E is an element of L. Okay. Well, that's more pristine than anything we've written up to this point. Is it pristine enough? Unclear. Now we need to consider, we need to strategize here, work out our tactics. How do we get from this innocuous expression up here to this horrible thing down here? Let's see. This is not so complicated, I think. So the first point will be we distribute this term R as an element of A. and then we step it down on let me see. So we need it for these two ordered pair terms, and we don't need it for anything else. Okay, I will mark that up here. That is the wrong color. Okay, and then I will indicate that we step it back down. On this term and on this term. Okay. And I will give light green. Okay, and then similarly, we're probably going to need that term for Spanish orange as well, I assume. It looks like we only need that for for this one term. So if I distributed that through, we would have P and Q or R. So we distribute to both and then immediately step down for this entire expression. Okay. And what we actually need for these is the distribution of this OR expression here. But we'll handle that on the next step. Right, so that's dark brown. Okay. All right, so what are we going to structure this as? Well, that immediately gives us the no, not quite, because we still have this OR expression that we have to distribute through, but roughly, yeah, it gives us. So we'll set this up for pattern matching immediately. Oh, what a finale. What a finale for the notebook. Let's see, enter derivable. So, supposing we can fit it in. Well, we're going to have to pattern match across the page because we need to do another step, which is distributing the OR. But okay, yeah. What a finale. Let's see. Not D equals the ordered pair as T. Or we have the AND expression in front, so we'll keep that. R is an element of A. And not the ordered pair SU is an element of R. Or R is an element of A. And so this should be a step down because of what we did with the AND distribution. And then it'll be a step down again when we take the quantifiers to existential statements. Or, well, yeah, not for this round, because these are already... no, yeah, these are existential statements. Okay, and not the ordered pair TU should be. No. TU is an element of R. Okay. Or D is an element of R. And so we don't need this AND expression, or yeah, we do. Yeah. We step it down for everything else. Okay, so D is equal to the ordered pair PQ. Yeah, we needed to be more inventive with our letter selection, but whatever, it doesn't make any difference. D is equal to the ordered pair PQ. And so for now, it's just the ordered pair term. The ordered pair PR is an element of R. And the ordered pair QR is an element of R. Or okay, so we would close this bracket, and now we open another. R is an element of A, and not E is an element of R. Not D is an element of R, rather. Okay, and then we close that bracket. Okay. And then we close and open, and we have the term or not R as an element of A. Okay. So now we distribute this through. Where this is or-wise associative, so when we distribute the or through, this term gets or'd onto this sequence, and we only combine it with this term. And then these two terms are or-wise associative, this sequence of ands, and then this term is or'd on. So then this becomes P or Q or R. Well, P or Q or R. And then we... Wait, what use do I make of that fact? Wait a minute. Right, then I only need to associate that with... wait a minute. This one doesn't quite work. And it's possible that for the same reason the others don't quite work. Why doesn't this quite work? Because when I distribute this through, we only need this term for these two. But we have to distribute it through to this. Maybe the journal editors won't notice. Let's see. Ow. I can just give myself the pattern matching anyway. It's a step down to these... It's not a step down... Actually, it's not a step down to these universal statements. But if I wanted the perfect pattern matching... I guess I could just put red on these two. Let's see. No, yeah, these would be the existential statements that we were supposed to step down. I'll just note. Okay, D is an element of R, or actually, this is out of order. And for the same reason up here. This is a little bit off center, but whatever. Okay. And then I will underline, I'll give that a little blue hat. Alright. And now, close here. Okay, and now we have and. Yeah, I don't know how that's to be avoided. We could just put a note under it, because we've typically given ourselves this would be a little bit of sleight of hand, but we've typically given ourselves the ability to generate terms like this. What do I mean? Statements like D is equal to an ordered pair, we've been willing to get rid of without dropping biconditional expressions, or without dropping interderivability claims, assertions. So the sleight of hand here would be that we could and down to get rid of this term, then distribute, and then get it back. Which is effectively a way of saying that when I perform this distribution, I don't have to distribute to it. I'll leave an asterisk. Okay, so... Okay. Now. Is it or? Hold on. No, it's and. Being extra careful here. Let's see. Not R is an element of A, or the ordered pair P R is an element of R, and not R is an element of A, or the ordered pair Q R is an element of R. Okay. Right, so once again the point is that if I distributed, so we have this and term, and then this term is or y is associative, so P and Q or R. So then when I no, hold on. No, it would be, if I distributed through the entire expression, I get P or Q and P or R. And then on the next layering, I get P or Q or R. And so we only combine this with P. So we distribute this term through P. Okay, so that should be fine. And then we have, though, to follow that up, we should close that and then open, and we have not R is an element of A, or D is an element of R. Okay, and then we can just dab a little bit of purple in there, a little bit of Parma violet. This is actually now our most, yeah, it's our smallest pencil because I've broken the lead on it so many times. The pigment, whatever. All right, and now I will say, well, let's do the pattern matching just as a matter of habit here. So this is going to be poppy red. And this is going to be orange. And this is going to be Spanish orange. And this is going to be true green. And this is going to be grass green. Where did grass green go? Grass green. Where did I put it? There it is. Okay. And then this is going to be whatever blue that is. This is going to be indigo. And you know what? I'll use violet blue instead of violet. Let's see what that looks like at the very end here. funny hats to there, there, and there. And here. Oops. Made a mistake. Alright. And the proof will get a little first the step down indicator. And then all right, and there you go. What time is it? Those are the exercises 20A through 20E. Actually, in this one, I'd say we did it fairly cleanly, without too many mistakes, but also much clearer than all of the preceding, which were both riddled with errors and ill-organized. Go grab another notebook. We only have about 7 minutes, but I'll get that going. This might have been record time. Alright, let's practice writing structure and interpretation, so I don't screw it up. Capital I. I'm gonna screw up that capital I. We could do lowercase. No, that didn't pass. Let's see. We wind ourselves up and we let ourselves go. And then we see what we do. And then we say, that was a mistake. Let me practice more so that when I wind myself up next time, maybe we won't make a mistake. Let's risk it. All right. Okay. Next exercise will be let R be the numerical relation such that the ordered pair xy is an element of R if and only if x plus y equals 1. Okay. Let A be the set of prime numbers between 10 and 20. Explicitly describe R pipe A. Okay. Then we've already done 22 through 24, and we've done 26 through 28. So we have to do 21, 25, and 29. Okay. See you soon.